In the late 19th century, electricity already existed, but only in fragile pockets of light. In cities like New York during the 1880s, power could illuminate a few streets, then quickly fade with distance. Early electrical systems depended on direct current, flowing in a single unchanging direction. The farther this current traveled from the generator, the more energy it lost to heat. This loss was not a technical flaw that could be patched. It was a physical limit that made long-distance transmission impractical, no matter how powerful the generator became. As cities expanded, the weakness of the system became impossible to ignore. Power stations had to be built close to users, locking electricity to geography. This was the environment Nikola Tesla entered when he began thinking about electricity not as a device, but as a system. The problem was not how to generate power, but how to move it. Until that problem was solved, electricity could never become a foundation of modern life. It could exist, but it could not yet be used at scale. Direct current flowed in a single fixed direction, which made early electrical systems simple but rigid. Once generated, the current had no way to adapt as conditions changed along the line. To deliver useful power at low voltage, direct current required very high current. That current immediately turned transmission cables into sources of heat. As distance increased, energy losses rose sharply. Most of the power never reached its destination, dissipating along the line before it could be used. There was no practical way to raise or lower voltage once the current left the generator. Without voltage control, the system remained locked into inefficiency. This limitation was not a matter of better engineering or improved materials. It was built directly into the physics of direct current itself. It was within this constraint that Nikola Tesla recognized a deeper problem. Electricity could be generated reliably, but it could not yet travel efficiently. Solving the transmission problem required more than a new generator or thicker cables. It demanded a different way of thinking about electricity itself. Nikola Tesla approached electricity not as a stream of particles, but as a changing field. He believed motion in a magnetic field could do work without direct contact. If a magnetic field could change over time, it could induce motion elsewhere. This idea shifted the problem from moving current to shaping fields. From this insight came the concept of alternating current. Electricity no longer needed to travel in one rigid direction. By allowing current to reverse direction in a controlled rhythm, new possibilities emerged. Voltage could be transformed, and distance no longer imposed the same limits. This was not a single invention, but a system-level insight. Nikola Tesla was redesigning how electricity behaved across an entire network. Alternating current works by changing direction many times per second. Instead of a fixed flow, electricity moves back and forth in a controlled cycle. This repeating motion creates oscillation in voltage and current. Energy is no longer locked to a single path, but shared across the system. Because the current changes continuously, its voltage can be transformed. This made it possible to raise voltage for transmission and lower it again for use. Raising voltage reduced the amount of current needed to carry power. With lower current, energy losses from heat dropped sharply. Power could now travel far from where it was generated. Electricity was no longer confined to short distances around power stations. Alternating current did not just improve efficiency, it changed electricity into something that could finally scale. The key to long-distance power transmission was the transformer. It worked by transferring energy between coils through electromagnetic induction without physical contact. Because the coils were electrically isolated, energy could pass while voltage changed safely. This separation made transformers reliable and scalable. Before transmission, voltage could be stepped up to very high levels. Higher voltage meant lower current for the same power. Lower current dramatically reduced heating in the wires. Energy that once vanished into cables now reached its destination. At the far end of the line, transformers reduced voltage again. electricity arrived usable, safe, and ready for work. This single component unlocked the entire AC system. Without transformers, alternating current would have remained an idea rather than an infrastructure. Electricity only becomes useful when it can be turned into work. In the early 1890s, converting electrical power into smooth, reliable motion remained a major challenge. Nikola Tesla solved this by creating a rotating magnetic field. Instead of forcing motion through sparks and switches, he let the magnetic field itself do the work. As the field rotated, it pulled a rotor along with it. Motion emerged naturally, without direct electrical contact or mechanical commutation. This eliminated sparks, wear, and instability. Motors became quieter, more durable, and far better suited for continuous operation. The rotating magnetic field was not a single device, but a principle. It allowed electrical energy to be converted into motion anywhere along the grid. With motors now integrated into the system, electricity became more than light. It became a universal source of mechanical power. A single alternating phase could deliver power, but it lacked stability under heavy load. Smooth motion required a system that could balance itself automatically. Nikola Tesla addressed this by using multiple phases of alternating current. Each phase was offset in time, creating a continuous rotational force. In a polyphase system, power never dropped to zero at any moment. As one phase weakened, another reached its peak, keeping motion continuous and stable. This balance reduced vibration, improved efficiency, and increased motor lifespan. Machines could now run longer without interruption. Polyphase power also made distribution more efficient. Loads could be shared across phases, preventing overload on any single line. This was the moment electricity became a true system. Generation, transmission, and use were finally designed to work together. Once electricity could travel efficiently, power plants no longer needed to sit inside cities. In the early 1890s, generation began moving closer to natural energy sources. Waterfalls and rivers became ideal locations for power generation. Energy could be produced where nature allowed, then sent outward through transmission lines. This separation changed how cities were built over time. Electricity no longer dictated where people lived or worked within the city. Power could now be delivered across regions instead of blocks. Distance stopped being an obstacle and became a design choice. Factories gained freedom from steam and coal. Motors connected directly to the electrical grid replaced centralized mechanical power. Electricity had become infrastructure rather than a local service. It was now a network designed to move energy wherever it was needed. Alternating current did not prevail because it was novel or dramatic. It prevailed because it obeyed the physics of transmission more efficiently than direct current ever could. By reducing losses and increasing reach, AC aligned engineering with natural laws instead of fighting them. Efficiency became a structural advantage, not an optimization. The system was flexible enough to adapt to different scales. It worked for small workshops, large factories, and entire cities without redesign. Standards formed around what worked reliably. Once adopted, the AC system shaped equipment, infrastructure, and industrial practice for decades. Direct current did not vanish, but its role narrowed. It became specialized, while AC carried the burden of distribution. The choice was not ideological or personal in nature. It was the outcome of a system that could scale without breaking under demand. Nikola Tesla did not invent electricity, and he did not claim to. What he changed was how electricity could behave once it entered a system. By redesigning the rules of transmission and conversion, electricity stopped being fragile. It became something that could move, adapt, and endure. This transformation reshaped cities, industries, and daily life. Energy could finally be delivered where it was needed, not just where it was generated. Electricity became usable when it became a system. And once energy could move freely, modern civilization followed.